This is lecture 11D for Calculus 2 on useful sequences and series. What I've done is put together some of the sequences and series that you will see over and over again. So instead of taking the test and then applying it to some sequence that maybe you'll never see again, I've tried to put together some of the famous sequences and series in this one lecture. If you get an understanding of these and how they converge, I think that will be a better background than just working through examples. So that's what I've done in this lecture. The sequences we're going to look at are the geometric sequence and see how it converges, then the harmonic and the P sequence, the alternating harmonic and P sequence, and then there's a few others that don't have names. When it comes to the series, we look at the corresponding geometric series and P series, the alternating P series, and then the telescoping series, which is always a good example. The geometric series occurs many places. This is what it is, the geometric sequence, I'm sorry. The sequence is a to the n equals r to the n, where r is a constant. Now this sequence converges or diverges depending on the value of r. And here's a list of the different cases. If absolute value of r is less than 1, then the geometric sequence converges to 0. If r is exactly equal to 1, then the sequence is 1, 1, 1, 1, 1, of course, and so it converges to 1. In the next two cases, it diverges. If r is equal to minus 1, then the sequence oscillates. It goes minus 1 plus 1, minus 1 plus 1 like that, and so it oscillates, therefore it diverges because of these oscillations never stop. And if the absolute value of r is greater than 1, that means r is strictly greater than 1 or strictly less than minus 1, then each term is bigger and bigger and bigger than the previous term. So it's an increasing sequence, but there is no upper bound. In this case, the geometric sequence diverges. The proof for all these is given in the textbook, and also I think I gave it for homework too. So here's your geometric sequence, r, a constant raised to the power n. And it converges or diverges depending on the value of r. The next sequence is in general, it's the P sequence, and a special case of the P sequence, that is when P is equal to 1, is called the harmonic sequence. So here is the P sequence. A to the n, the terms a to the n equals 1 over n raised to the power p. This is similar to the geometric sequence, except not only is it there's a reciprocal here, but also the order of the n of the index and the constant are reversed. Remember that for the harmonic sequence. Let me get the pen here. Here's a harmonic sequence. Here's a geometric sequence so you can remember. A to the n equals r to the n. R is the constant. For the P sequence, P is the constant, and the index n is raised to the power p. Here, the constant is raised to the power n. For the special case of p equal to 1, we have the harmonic sequence. The terms of the harmonic sequence are a to the n equals 1 over n. If p is greater than 0, the P sequence converges to 0. That means all these terms will be getting smaller and smaller and smaller, and if n goes to infinity, they approach 0. By terms, I mean the whole thing, because the denominator is getting bigger. The frequent use of this is to isolate terms 1 over n to the p out of complicated sequences. That's a big application of these P sequences. Let's look at the precise definition of the oops, sorry, I missed the marker. Let's look at the precise definition of convergence to see if we can prove the result about the P series, or P sequence, sorry. You have different results for the P series than for the P sequence. All right. The precise definition of convergence says there exists some n for any epsilon greater than 0, such that for all terms a to the n where n is greater than n, the difference between the term and the limit is less than epsilon. Here we're saying that the limit is 0. Well, let's note that n is non-negative, okay? So we have a to the n minus L, the absolute value, is 1 over n to the p minus L, but L is 0, so this becomes the absolute value of 1 over n to the p. N is non-negative, so this is just 1 over n raised to the p to the power of p is less than epsilon. Okay, this is a statement we need. We need to find a capital N such as this holds. Okay, well, for all n greater than 1 over, we isolate the n out of this equation, for all n greater than 1 over the pth root of epsilon, this result is true. So we let big N be 1 over the pth root of epsilon. And this gives us n. As long as p is greater than 0, this sequence converges, and it does converge to 0. What happens if p is less than 0? If p is less than 0, then we have 1 over n, let's say, to the minus 2. Okay, this is n squared. The limit of this is infinite. It diverges. But 1 over n squared converges. How about n to the 1/2? That will converge as well. Remember that n is getting much larger. This is a very large number. As n approaches infinity, well, it becomes infinite, and it converges to 0. So the terms of the p sequence converge to 0 for p strictly greater than 0. What happens if p is equal to 1? Okay, p is equal to 0. If p is equal to 0, n to the 0th power is 1, and then the terms are 1, 1, 1, 1. Okay, in that case, it converges to 1. Here's an example of the use of the results for the p sequence. Let's say we want to investigate this particular sequence. A to the n equals 1 minus 2 times n over 1 plus 2 times n. Let's do an algebraic rewrite of the sequence before we take the limit, or as we take the limit, and use the results for the convergence of the p sequence. Okay, so what I'm going to do is divide numerator and denominator by n. When you have these kind of fractions, divide by the highest power of the n if you have a sequence that looks like this. Okay, so when I divide, I get 1 over n, a harmonic sequence, minus 2, over a harmonic sequence, plus 2. Well, taking the limit of the harmonic sequence is 0. Move the pin here. So this limit is 0. This limit is 0. Of course, the limit of 2 over 2, minus 2 over 2 becomes minus 2 over 2, and the result is minus 1. Here's another example. Let's look at this sequence here, where the terms a to the n are 4 n to the 5th power minus 6 over 7 n minus n squared. Right. To use results from the p sequence, we're going to divide numerator and denominator by n to the 5th. Divide by the highest power. That's the rule or trick here. Okay, the result is 4 minus 6 over n to the 5th. Okay, what do we have here? P sequence with p equal to 5. Then we have 7 over n to the 4th, which is a p sequence with p equal to 4. And here's minus 1 over n cubed, which is another p sequence with p of 3. Now, in taking the limits, of course, the 4 is constant. This limit is 0 because the p sequence converges to 0 for p greater than 0. This one is 0, and this one is 0. All right, so the result is it diverges. Here's a third important sequence, and this is the alternating harmonic and p sequence. So the alternating p sequence is a to the n equals minus 1 raised to the nth power over n to the p. So this is just the p sequence with the terms alternating minus 1 plus 1 minus 1 plus 1. Okay, or that's multiplying the terms. The alternating harmonic sequence has is the same with p equal to 1. So here's your alternating harmonic sequence. Both converge to 0 for p greater than 0. Let's prove that. To prove it, we'll use the results for the p sequence. So, and we can use the squeeze theorem. Minus 1 to the n divided by n to the p is less than or equal to 1 over n to the p. Each term, I think that's pretty obvious to see that this is true. Okay. And of course, this original sequence is greater than or equal to minus 1 over n to the p, raised to the p. Okay, so now here's the squeeze setup. 1 over n to the p minus 1 over n raised to the pth power. Let's take the limit of both of the flanking sequences, and both of them converge to 0. It doesn't matter that it's multiplied by minus 1. It's going to converge to 0. So the sequence that's sandwiched between the two will also converge to 0. So by the squeeze theorem, the alternating p sequence converges to 0. And this result holds for all values of p where 1 over n to the p converges to 0. And that would be for p strictly greater than 0. Notice that if p is equal to 1, what do we have? We've tried to set up this squeeze theorem with p equal to 1, right? Then we have 1 over, I'm sorry, with p equal to 0, 1 over n to the 0, all the terms are going to be 1s. So minus 1 over n to the 0 is just going to be minus 1, minus 1, minus 1. Okay, the result, that doesn't sandwich the sequence properly. It blanks it, but it doesn't sandwich it because both of these do not converge to the same limit. One converges to 1, and the other is a convergent sequence to minus 1. If you remember with the sandwich theorem, the two sequences on the outside both have to converge to 0. Actually, that's not true. Both sequences that flank the original sequence have to converge to the same limit. In this case, they don't converge to the same limit. One converges to 1 plus 1, the other converges to minus 1. Okay, so here's our second unnamed sequence, and we're looking for a sequence a to the n equals n to the nth power. And the limit is 1, and we want to prove that. So we're going to prove that using logarithms. Let's take the natural log of both sides. Natural log of a to the n equals the natural log of n raised to the nth root. Okay, if I take taking the natural log, of course, the exponent 1 over n comes out in front, and we have that form that we used, that we just looked at on the other page. So this is equal to, of course, natural log n over n, and we know its limit. We know its limit is 0. So by that result, we know that the limit as n goes to infinity of the natural log of a to the n is 0. But of course, we want to know the limit of a to the n itself. To find that, we use exponentiation. So let's raise both sides by e, and e to the 0 is equal to 1. Of course, this is e and the natural log, which is why we chose those two. Hence, the limit as n goes to infinity of the sequence n raised to the 1 over n is equal to 1. So in this case, we used our previous result here. We used logarithms, the previous result, and then exponentiation to find our answer. Now let's look at the sequence x raised to the 1 over n. And we want to find the limit. And I'm saying here that that limit is 1 as long as x is greater than 0. So again, we're going to use logarithms, remembering that x is a constant. So the natural log of a to the n equals the natural log of x raised to the 1 over n. The 1 over n comes out, and we have natural log of x, which is a constant. Right? Now take the limit. Right? Natural log of x comes out in front because that's a constant. Let me get the pen here. So here we have a constant. Remember, on the other slide, we had the natural log of n itself. That's not a constant. Here it's natural log of some number x. So the natural log of x comes out in front. Then we have the limit as n goes to the infinity of 1 over n. Right. Now the limit of this harmonic sequence is 0. So we have 0 times the natural log of x. Of course, x has to be greater than 0. We couldn't have, this would not have been defined if x was less than 0. So here we have a result of 0. Again, we used exponentiation to find the limit of a to the n itself, and a to the 0 is 1, so that's our limit. And I'm writing here for x greater than 0. Otherwise, we couldn't have used this technique of taking logarithms. I'll just present the next two sequences, the unnamed sequences, without proof. Otherwise, this lecture could go on forever. All right, the sequence in this case is a to the n is 1 plus x over n. And then we're going to take the limit as n goes to infinity, and that is equal to e to the x itself. And here's another one. A to the n is x raised to the nth power divided by n, where n is a constant, and that limit is 0.